Hi, so basically I'm going to discuss a number of different projects that all include how you can utilize fossils in order to indeed calibrate the time tree of life. My background is in arthropod phylogeny, and it's obviously an exemplary clade to use for this sort of purpose because they have so many exceptionally preserved calibration fossils, and we can know their relatively precise identity with respect to extant clades, and we reviewed this in an extremely long paper with Greg, and I don't know if Ali is somewhere in the room, but we just published this year, so if you want to read a paper that's longer than my dissertation, we did that. And so there's a lot of arthropods that we can calibrate the tree with. And generally, these were all fossils that could be expected to calibrate the nodes of extant clades in the traditional formulation where you have a molecular phylogeny and you're just adding an age prior onto each node, like the first molecular clock analysis that I was involved with. And there are still quite many arthropods that you can include in this. However, there are a lot of new methods that have begun to be introduced that directly incorporate the fossils into the phylogenetic topology as well as into the age modeling, some of which Rachel talked about earlier. So we have to accommodate the fossil age uncertainty when we're doing this. So you can construct the age prior by determining the minimum age, which in this example will be coming from correlation between the locality where the fossil was derived and then global correlation to eventually get an absolute number. And maximum ages for node calibrations usually come from node bracketing, so determining that the age cannot be older than the previous clade, or in this case, that there were no ostracods, for example, in the British Shale, so it's probably not older than that. But for tip dates, where you want to include the fossils directly into the phylogenetic analysis, those you then have to actually infer the maximum possible age of this species, not the clade. And that's usually also coming from the formation. So you get a much narrower range there. So I decided to investigate the influence of arthropod fossils on divergence time estimates. And this is purely from morphological data. So I used the matrix that David Legg put together that was the most recent version from Derek's paper, which published at Palaeontological, I think that's how it's pronounced. And I constructed the topology under Bayesian and parsimony methods. And indeed, there was a pretty big difference. So the chelicerates were monophyletic in parsimony, but not exactly in Bayesian. And then myriapods were fine. Pancrustacea was actually not found in the Bayesian because the yellow is the hexapod. So we actually have this situation where the hexapods and myriapods are together there. I think what we're observing with the Bayesian, also notice that this sort of polytomy here includes all these stem numbers. I think this is the same case that's in the placoderm paper that just came out in SysBio. I haven't read it really closely, but the Bayesian methods are supposed to have higher accuracy, so you're not getting the wrong topology erroneously, but it's not very precise, it's not well resolved. And perhaps the parsimony topology, all the nodes are resolved, but maybe they're the wrong nodes. So I decided to just do the inference on both. And I did this with tip and node dating, and then with uniform tree priors and fossil birth death priors as well. So the preliminary age estimates that we got, I've got to admit almost nothing of this has converged because I was doing it like this weekend. But I'm seeing the blue are the node dates, and then the purple and pink are all the tip dates. And all the tip dates that I observed is the same thing that has been seen in other analyses of other clades, where they're quite a lot older. And all the fossil birth death models seem to be giving greater precision. Now, I don't really think that the priors that I have for fossil birth death, particularly on things like speciation rate and fossil recovery rate, I don't think any of that is meaningful in a data set like this, where we have like 300 taxa for all of arthropods. Obviously, there's like over 1 million arthropods. So I'm not really sure that either of those methods are very meaningful with these data. I'm actually going to say that I'm more comfortable right now with the type of estimates that we can get with this sort of data set from node dating. And maybe what we're seeing is a bit of model inadequacy to use only morphological data, which has been termed deep root attraction in Fred Ronquist's paper. So certainly to do these sort of analyses, I think I need to more closely look at what we can actually get empirically to include in the fossil birth death priors. And we also have to realize that morphological evolution is not going to be clock-like necessarily. And I think that with a lot of these, the really old estimates that we're seeing in some of these is because there's so many stem taxa that with the tip dates, it is forcing there to be a slight branch length. And it's just so additive that it's pushing the whole root down. Similarly, we have a lot of dependent characters, and Ronquist noted that things like where you have a character that's about the structure of an exopod, but obviously you can only code this in a taxon that has an exopod on that limb. None of the modeling is accounting for that. One thing that he suggested to do would be to increase the cost of ghost lineages. I haven't explored that yet. But I do think that we have some reasonable estimates from this data that are concordant with what's been seen in molecular clock node analyses. So that's good news because I'm going to spend the rest of the talk on node dating analyses in sort of the deep yonder, because the tree of life as a whole actually quite predates fossils. And arthropods are a great clade, and I love them more than anything. But the fact is, if you want to date the whole tree, you don't really have fossils past a certain point, and bacteria and Archaea have almost no fossil record at all. So I've been involved now with a project at MIT, this is technically what I get paid for, in how you can date microbial tree of life in the absence of fossils. And so one of the clades that we're interested in is the proteobacteria, which comprise a large part of the microbiome of humans. And actually these little dots sort of around a circle are showing the differential priority of each microbial clade depending on what tissue of the body it's found in. And the way that one of the ways that we're calibrating this is actually from Host-endosymbiont, cospeciation. We certainly didn't invent this, but I think we're the first people to actually really be applying it in a molecular clock analysis. So the concept is this. You have the host phylogeny, because we know that microbes live within the cells and the bodies of various hosts, including ourselves. So say it's within arthropods. You have the phylogeny of the arthropods. And if the phylogeny, the molecular phylogeny of the bacteria that are within it is the same, then you can actually apply those arthropod dates onto the same nodes in the molecular tree of the bacteria. And so it will improve the age estimates of the whole thing. So we did this in the proteobacteria, and we found quite a few. They're just these shallow ones up here. I'll talk about how we got these a bit later. But even within this, it got some actually interesting, I'm not going to talk about that, but it got some interesting age estimates for these two purple clades highlighted, which I'm going to show here. So the Vibrionalis and the Enterobacterialis are both clades that are really important in our own microbiome and in disease and so on, and they're found throughout different metazoans as well. And I really truly didn't make this up. This is actually aligned right here with, like, look at the reasonable precision on that. This is showing the clade originated at the exact same time when all of the various animals and multicellular organisms were starting to occur. So we're starting to see from multicellular organisms to organisms with differentiated tissues and, of course, completely metazoans. And at that same time is when this clade that we know lives differentially within different tissues of our bodies is starting to originate and diversify. I think that's actually a really exciting result. I'm really happy about that, and I'm hoping that we're going to get even greater precision on this soon. So yeah, the evolution of animals is actually the evolution of habitats for these guys. But we can step out even older than that. And so the question that we were addressing was whether methane could have been a greenhouse gas in the Archaean. This is like way beyond anything in the fossil record, right? And the concept of it was mostly that the sun was less luminous at the time in the Archaean, yet it's estimated that the Earth was in fact covered with liquid water. Why wasn't it frozen? Why was the Earth warm enough? Probably because there were greenhouse gases, but how could they have been produced? Right now, the biggest production of methane is coming from the metabolism of Archaea, the clade. But we don't necessarily know whether they were around at that time. So we came up with a little nifty thing to do that harnessed, because there's no fossils for these, but it harnessed the way that molecular data works in bacteria and Archaea, because they are exchanging their genes through horizontal gene transfers like this. So we called it TARDIS. This was the first time we went through review. They told us that we were pompous. Literally, a reviewer told me I was pompous. And I'm not allowed to call it a method, and I'm not allowed to name it. So it's only going to be in talks now. Sorry, guys. but basically you have a gene transfer, this is a molecular tree, from one clade into another, and say that that second clade is fossiliferous. Then what you can say is the donor clade must be older than the clade that it has donated a gene to. So you can therefore apply the age of the fossil to this node and sort of use that to infer the divergence times and actually calibrate the tree for a clade that has no fossils itself. So we did identify within Archaea, and the red lineages are all different methanogens of Archaea, and we identified a gene transfer from there to Cyanobacteria. So I've got to back up and say that Cyanobacteria is actually pretty much the only microbial, like prokaryotic clade that has anything resembling a real fossil that we can sort of identify. So there are a few different ones that have been discussed in the literature, and these are actually to scale here. So they're both a similar structure that's called an acone. It's observed in a certain clade of extant Cyanobacteria, which is called Nostocalis. And both of these have been purported to be potentially members of Nostocalis, but Nick Butterfield sort of argued against the smaller one being an appropriate calibration because it's so tiny, and actually there's not that many characters there, and size is one of the characters. But other people have sometimes used this to discuss the evolution of cyanus. So I decided to see what would happen if you calibrated it on both of those ages. And so these are estimated node ages. Green is for Cyanobacteria, and then red is for the methanogens, and then gray is for the actual root of this tree. So it includes the gene transfer to Cyanobacteria within the tree. And then the 1.2 billion year old is the big, more appropriate fossil, and then the 2 billion is the smaller, less appropriate fossil, and then I sort of simulated every age in between as well. And what we find is that after a certain threshold, around 1.6 or 1.7 billion years old, the calibration basically screws it up so much that you get the root of the tree being older than the oldest boundary on the root prior. So the oldest boundary we got from 4.4 billion years old, which is the oldest zircons and the oldest rocks found on Earth. So I don't really want to be saying that this molecular clock is inferring panspermia, because that's a bit outside what we're doing here. So I think this is sort of circumstantial evidence that the 1.2 billion-year-old calibration is more appropriate. And so we were able to then to actually show this divergence time analysis, which contains all these methanogenic archaea. It contains the cyanobacteria that have been horizontally transferred, and it contains this fossil within it at 1.2 billion years old. And you see that the methanogens would have emerged in basically the earliest Archaean, which does suggest that this being the minimum age from the youngest fossil that we had, that they would have had to have been around in the Archaean. So it was indeed possible that microbial methane was a really big contributor to warming of the early Earth. So I've kind of gone through quite a lot of Earth history in one talk, but I think this is really great, and I think it illustrates why we as paleontologists are really important. We still have to know the morphology and the systematics of fossils. We have to know about their stratigraphy because they're essential to calibrating anything from the oldest microbes to the rise of oxygen, the origins of multicellularity and the bacteria that infect them, as well as actual animals. And all of this is really dependent on knowing the fossils and their place in phylogeny. So I think it's good news for us. All right, thanks everybody.